2 billion people open Instagram every month to scroll an endless feed of photos and videos. So how do you actually build something like that? Today we're going to design Instagram from scratch, the same way you would in a real system design interview. We'll keep it tight, move fast, and build it one clear piece at a time. Let's go. First, the single most important insight. The hard part of Instagram is not storing photos, it's serving the feed. For every person who posts a photo, millions of people are scrolling and reading. The system is overwhelmingly read-heavy, often 100 reads for every single write. So our entire job is to make feed reads blazing fast, even if that means doing extra work when someone posts. Keep that ratio in mind because every decision flows from it. To stay organized, we'll follow a clean blueprint called RESHADED. Requirements, what it must do. Estimation, the rough scale. Storage, the data model. High-level design, the architecture. APIs, the contracts. Detailed design, the hard parts. And evaluation, the trade-offs. 7 steps. Let's take them one at a time. Step 1, requirements. Before we draw a single box, let's agree on exactly what we're building. Here are the functional requirements, the core features. 1, a user can upload a photo or video with a caption. 2, a user can follow other users. 3, each user gets a personalized home feed of recent posts from the people they follow. And 4, users can engage with likes, comments, and stories. Upload, follow, feed, and engage. That's the heart of the product. Now the non-functional requirements, the qualities that make it feel great. It must be highly available. The feed should basically never be down. It must be low latency. The feed has to load in a couple hundred milliseconds. It must scale horizontally to billions of users and their photos. And here's a key one for the feed: we can accept eventual consistency. If your friend's brand new post shows up a few seconds late, that is completely fine, and that flexibility buys us enormous scale. Step 2, estimation. Let's do quick back of the envelope math to feel the scale, because the numbers will justify our whole design. Let's size it. Say we have 500 million daily active users. If even a fraction post, that's roughly 100 million new photos every day, which works out to over 1,000 uploads per second. But reads dwarf that. With 100 to 1 read to write ratio, we're serving on the order of 1 million feed reads per second at peak. On storage, if an average photo plus its resized versions is around 2 megabytes, 100 million photos a day is about 200 terabytes of new images every single day. The takeaway: this is a read-heavy, storage-hungry firehose, and that demands aggressive caching and a content delivery network. Step 3, the data model. Let's figure out what we store and, crucially, which type of database fits each piece. There are 4 core entities, and the trick is to pick the right store for each. Users, the profile data fits a classic relational database. Media, the metadata for every post, the caption, author, timestamp, and the photo's URL is a relentless firehose of writes, so it goes in a wide column store like Cassandra. The follow graph, who follows whom, is best served by a graph style or key value store optimized for fast lookups. And the feeds themselves live in Redis and in memory cache, so reads are instant. One golden rule: choose your database to match the access pattern, not the other way around. Step 4, the high-level design. Now let's draw the architecture, following the 2 journeys that matter: posting a photo and loading a feed. Here's the whole system in one picture, and notice it splits into 2 paths. The right path, when you post, goes through the gateway to an upload service, which stores the original in object storage like S3, kicks off background processing, and pushes the result to the CDN. The read path, when you open the app, goes to a feed service that reads your pre-computed feed from Redis, joins in the metadata, and hands back image URLs. The actual images never touch our app servers, they're served straight from the CDN's edge. That separation is what lets each path scale independently and keeps the app servers completely stateless. Step 5, the APIs. Let's nail down the 2 contracts the clients actually call. There are really just 2 interfaces that matter. The write is a push. You post your media, and critically, the server accepts it and returns immediately, with the heavy processing and feed fan-out happening asynchronously in the background, so your app never freezes on a slow upload. The read is a pull. You get your feed with a cursor, which gives you clean, stateless, infinite scroll, 20 posts at a time, and it hits the cache before it ever touches a database. A simple push-in, a cheap, paginated pull-out. Step 6, the detailed design. This is where interviews are won. Let's deep dive into the hardest problems that decide whether this thing scales. Deep dive number 1, the media pipeline. When you upload, we store the original exactly once. Then a fleet of asynchronous workers picks up the job and transcodes that one photo into several sizes: a tiny thumbnail, a small version, a medium, and a large one. Why? So we can send a phone a lightweight image and a desktop a crisp one, saving massive bandwidth. Every version is then pushed out to the CDN, so the photo is cached on an edge server geographically close to each viewer. Upload once, serve from everywhere. Deep dive number 2, the famous one, how do we actually build each user's feed? There are two classic approaches. Fan out on write, also called push, means the moment you post, we immediately insert that post into the feed of every single follower. Reads become instant because the feed is already built, but there's a catch. Fan out on read, also called pull, does the opposite. We build nothing on write and instead gather posts from everyone you follow the moment you open the app. Writes are cheap, but now every feed load does heavy work. Each approach has a fatal flaw at scale. And that flaw is celebrities. If a star with 100 million followers posts, pure push means 100 million writes for one photo, a write storm that can take down the system. So the real-world answer is a hybrid. For normal users, we push, fanning their posts into followers' feeds since that's cheap and keeps reads instant. But for mega accounts, we skip fan out entirely and pull their posts in at read time. When you load your feed, we merge your pre-computed feed with fresh posts from the big accounts you follow, run it through a ranking model for relevance, and serve the result from cache. Push for the many, pull for the few. That hybrid is how Instagram really works. Deep dive number 4, sharding the database. A single database can't hold billions of posts, so we split it across many machines, choosing a shard by hashing the user id. This scales writes horizontally, but it creates a sharp danger. If one shard happens to hold a celebrity with 100 million followers, all that traffic slams into a single machine. We call this a hot shard, and it can take the whole system down. The fixes are essential. Use consistent hashing so we can add machines without reshuffling all the data. Add red replicas to spread those hot reads across copies, and treat the biggest accounts as a special case so a single star can never melt a single shard. Deep dive number 5, and for a red-heavy system, this is the whole game. Caching, we cache at every single layer. The client remembers your recently seen feed and images. The CDN caches every photo and video at the edge close to you, and Redis caches the feeds themselves, your session, and hot counters like counts. A read cascades down through these layers, and only if every cache misses does it finally touch the database. Done well, the cache hit rate is around 99%, which means the vast majority of reads never reach the database at all. That is precisely how we serve 1 million reads per second without falling over. Before we wrap, let's acknowledge that a real Instagram is more than just the feed. The same building blocks, storage, caching, fan out, and queues power everything else too. Stories use the same media pipeline but with a 24-hour expiry. Direct messages need a real-time messaging service. Explore and search lean on Elasticsearch and ranking models. And likes and comments are high-volume counters that we update asynchronously and count approximately at the extremes. Same toolbox, new features. Step 7, evaluation. Every design is a set of trade-offs, so let's name them honestly, then map it all to real tools. 3 trade-offs you can't escape. First, push versus pull for the feed. We chose a hybrid because neither pure strategy survives celebrity scale. Second, consistency versus availability. We chose eventual consistency for the feed, accepting a few seconds of delay in exchange for an always-on, lightning-fast experience. And third, storage cost versus speed. We deliberately store multiple copies of every image and cache aggressively, spending disk and memory to buy the low latency that keeps users scrolling. Good design is choosing your trade-offs on purpose. Finally, let's map every layer to the real tools you'd actually name in an interview. Clients and an API gateway at the edge. Stateless app servers behind a load balancer, object storage like S3 for the photos, a CDN like CloudFront or Fastly for delivery, Cassandra or sharded Postgres for metadata, Redis or Memcache for caching feeds and counts, Kafka and a worker fleet for the asynchronous fan-out, and Elasticsearch for search and explore. Each piece does one job and does it well. So let's bring it home. We started from one fact: Instagram is massively red-heavy. We followed RESHADED end-to-end. We split the system into a write path and a read path, stored each entity in a database that fits its access pattern, built our media pipeline around resized variants in the CDN, and solved feed generation with a hybrid push-pull design plus heavy caching. That right there is a complete, scalable design for Instagram. Thanks for watching, and good luck in your next interview.